Hello and welcome. Today we're going to talk about Chapter 3 or Module 3, the fundamentals of cryptography. This is a fun concept because you're going to learn in a brief way about the behind the scenes of how things are secured using the encryption. So, we want to be able to define cryptography by the end of the module. Describe what a hash, symmetric, and asymmetric cryptographic algorithms are. List the various ways in which cryptography is used. And explain the different cryptographic limitations and attacks. So those are our goals. So, let's talk about stenography, which is the process of hiding the message. So, it hides the existence of data. So maybe you put the data in a picture, audio, video, which can contain the hidden message embedded in it, and then extract that information later on. So all you might be looking at is a picture of an apple, but it would have important information embedded in there. And what it does, it's achieved by dividing data and hiding in unused portions of the file. Common scheme is to hide the data in the file header fields that then describe the file between the sections of the metadata used to describe the content or structure of the actual data. So cryptography is the practice of transforming or scrambling information so its meaning cannot be understood by unauthorized parties. Remember, go back to our CIA security. You have your confidentiality, integrity, and availability. So one method in cryptography is transposition, which each letter of the message is then rearranged. So like you would take the word hello and rearrange all the letters. Or do what's called substitution, where one letter is substituted for another letter. Okay. For example, if we have the word, if we took out every letter of the alphabet, A through Z, and gave it a number 1 through 26, and this is the beginning of what's called the Caesar cipher, or the simplest of the symmetric encryption methods. So I have the word cat, C-A-T. So if I used a key in my encryption of, say, the number 1. So that means for every letter that I encounter, I'm going to add 1 to that letter. So the word C-A-T becomes D, C becomes D, A becomes B, and T becomes U. So my cat, C-A-T, becomes DBU. So I have a very nice DBU. Someone might say, gee, what is a DBU? Because they don't know what that is. They don't understand that. Only those people that have the key to decrypt it, to change it back from a D back to a C, B back to an A, U back to a T, so changing my DBU back to a cat. Okay? So the process of changing the original text into scrambled message is known as encryption. So anytime you change that from the original message, which is called plain text, the unencrypted data, and encrypt it, it becomes ciphertext, the scrambled and unreadable output of encryption. And clear text is the unencrypted data that is not intended to be encrypted. So you have basically in your encryption, you have your plain text and ciphertext. So plain text data is input into a cryptographic function, also called cipher, which is a series of procedures based on a mathematical formula used to encrypt and decrypt the data. It uses a key, which is a mathematical value entered into an algorithm to produce that ciphertext. Just like we changed our CAT to our DBU, our key was the number 1. The reverse process uses that key to decrypt the message. So a critical factor in cryptography is that one or more elements must be kept secret at all costs. So you have to keep that key private. Don't let anybody know about it. Okay. So this is what it looks. It's almost like, everything related to computers, some kind of input, processing, and output. Okay, so here's an example of a confidential memo. Layoffs at the Lakeview store will begin, ... So we want to have our encryption algorithm with whatever the key is there. And you see it changes into that ciphertext, which is unreadable information. And then we transmit that cryptographic information to the remote user. And they use that same key and they decrypt it. And it comes back as confidential memo. Layoffs at the Lakeview store will begin. So that's your process. That's your encryption on the top and decryption on the bottom. On the left-hand side is the plain text. On the right-hand side is the ciphertext. So, some benefits of cryptography. Why do we do this? Well, cryptography can provide the following security protections. Again, you have your confidentiality, your integrity, and your authentication. You also have, if you use what's called the public-private key encryption, you can have what's called non-repudiation, which proves the user performed an action. So if somebody sent an email and then they later deleted it and says, no, I didn't send it, well, we can prove that with that public-private key because their signature is in that email. Also, obfuscation, which means to confuse, making something obscure or unclear. So that's the whole process or premise of the encryption. You're utilizing security through obscurity. So it's where virtually any system can be made secure as long as the outsiders are unaware of it or how it functions. Okay, here's our first check activity. Layla encrypted a document so that it can only be viewed by those who have been provided the key. What protection has she given to this document? Is it confidentiality, integrity, authentication, obfuscation? Well, let's take a look at it from a point of view, ruling out what it might not be. There was no mention of the fact that the documents changed, so we can probably rule out integrity. Obfuscation, that's what encryption's doing. But the key here is it can only be viewed by those who have been provided the key. Okay. So would it be confidentiality, integrity, authentication, or obfuscation? Well, when you go back and double check, it's the confidentiality. So it's confidential that only the authorized parties can view the information. So if I don't have that key, I don't care how great whatever it is that you encrypted, I can't read it. It's just gibberish. So the encrypted information can only be viewed by those who have been provided the key. That's an example of confidentiality. So always remember that. Okay. So you have different cryptographic algorithms, and I want you to put a star, maybe a double star on this slide. This is when anybody talks about cryptography, this is one of the key things. So how are you going to do it? Are you going to use a hash algorithm, a symmetric algorithm, or an asymmetric algorithm? These are the three ways to use cryptography or make three cryptographic algorithms to encrypt things with. So you've probably heard about hashing like MD5 and so on. symmetric, you've heard of things like DES, 3DES, AES. Okay. And the asymmetric, that's your public-private key cryptography, where each party has two keys, a public key and a private key. Sometimes you've heard of like RSA security, or RSA for the encryption. So there are variations of the algorithms. In a secure cryptographic algorithm that's hand calculated, okay, it's a one-time pad. It combines plain text with a random key. The pad is a long sequence of random letters. To decipher the message, the recipient must have a copy of the pad. So a stream cipher takes one character and replaces it with another. A block cipher manipulates an entire block of plain text at one time. And a sponge function takes as input a string of any length and returns a string of any requested variable length. So your hash algorithm, it creates a unique digital fingerprint of a set of data commonly called a hashing. This fingerprint, called a digest, sometimes called a message digest or a hash, represents the contents of that plain text. Now it could be a simple few words, it could be one long word, it could be an entire file, whatever the case might be. It's primarily used for comparison purposes, like when you download something, maybe it's a very long file, a song, or some kind of download. Then they give you a MD5 hash that you can compare it with. So when you run the MD5 hash, the result that you get, you can compare with what the author put out there, and if they're the same, then you know you got the correct file without any problems. Hashing is intended to be one way, so its digest cannot be reversed to reveal the original set of data. So it also uses what's called compression. So it might take supercalifragilisticexpialidocious, or the quick brown fox jumped over the lazy dog, and depending if whatever hash style you use, it's going to create a smaller file. So you're taking something large and reducing it down to something small. So here's some examples of hash algorithms: SHA, RIPE-MD, Whirlpool. Okay. And again, it's often used to check and verify the original contents of if an item has not been changed or not. Okay, so here's an example of the hash value. You have SHA1, SHA256. Okay, and you can see that in there. So your next one is your symmetric. Symmetric meaning the same. So the same key to encrypt it is the same key to decrypt it. It's also known as private key cryptography. The problem is, guess what? If I have to talk to someone in California via the internet, how do I tell them this is my key that I'm using to secure my file? I'm not just going to open the window and shout it. Anyone who's within earshot or who's between me and California will know the key to decrypt the file. So that's one of the weaknesses. It does very good encryption. So it can provide strong encryption if the key is kept secure between the sender and the recipient. So here you have advanced encryption standard, the AES I mentioned before. You have Blowfish and Twofish. Those are different encryption standards also. So here's an example. You have your plain text, you have your encryption algorithm, that's your key, and then that generates the ciphertext. You transmit the ciphertext, the person receives it, they unlock it with the key, and you see the plaintext. So this is symmetric, meaning the same key to lock it or encrypt it is in there to decrypt it. Next is we have our asymmetric. Asymmetric means we have one key to lock it and one key to unlock it. Okay, it's also known as public key cryptography. And you can see the primary weakness of symmetric algorithms is that distributing and maintaining a secure key among multiple users poses challenges. Okay, so now we have the use of two mathematically related keys known as a public key and the private key. So public key is available to everyone and is freely distributed. The private key is known only to the individuals to whom it belongs. So, in asymmetric cryptography, you have certain principles regarding that. You have key pairs, again a public key and a private key for both the sender and the receiver. So you're going to have technically 4 keys. So a public key is again the one that everyone knows, a private key only you know. So if person A wants to send a message to person B, we'll see this here in a little bit. The person A has to encrypt the message with person B's public key, and person B has to read it with their private key. So this is what it looks like. So Bob, the sender, wants to send a message to Alice, and Bob has to use Alice's public key to encrypt the message. And then is going to send it to Alice, and Alice is going to decode it with her private key. And then when she replies back to Bob, if she does, then she's going to encode the reply with Bob's public key and then send it to Bob, and when he receives it, he's going to decode it with his private key. Okay. RSA is an asymmetric algorithm that was published in 1977. Asymmetric meaning different, so it's not the same one key to encrypt and another key to decrypt. It uses, there's a elliptic curve cryptography. Users then share one elliptic curve at one point on that curve. It uses less computing power than a prime number based on asymmetric cryptography because the key sizes are smaller. All modern operating systems and web browsers rely on ECC. This is what it would look like if you drew an elliptical curve. That means you're going to find a point on this graph that's going to be the encryption of whatever value you're coming up with, whatever plain text that you want to encrypt. So you also have what's called digital signature algorithm. So it creates a digital signature which can do the following: verify the sender. This, we talked about that as the repudiation, to prove that it was something was sent from a particular sender. So that way you can prove that they're preventing them from disowning the message. You have key exchange. You have Diffie-Hellman ephemeral, elliptic curve Diffie-Hellman, and perfect forward secrecy. Okay, so here we come with our check activity. Which algorithm uses the same key to both encrypt and decrypt? So that should jump out right at you. Boom, boom. Same one. It's not going to be A or B or even C, because it's going to be D, symmetric key cryptography. Whenever you hear the word same key, that's symmetric. Okay, symmetric cryptography. Same key to encrypt and decrypt the data. And it's almost easy to remember, same key, symmetric. different key asymmetric. Okay. So now let's take our encryption and expand it so it can protect our computer, protect the file system, the operating system. You actually can encrypt your hard drive, but you can and you can see where some people encrypt their servers, databases are encrypted and things like that. But as you do those things, always remember, keep in mind, it's going to add time. So your lightning fast computer system is not going to run just as lightning fast as it used to, because it's taking a few extra microseconds and encrypting and decrypting the data on the computer. So encryption software can be used to encrypt the data and decrypt files one by one. That's file level encryption. Protecting groups of files can take advantage of the operating system's file system. Third-party software tools available for encryption include GNU, Privacy Guard, AxCrypt, FolderLock, and VeraCrypt. Microsoft Windows has encrypted file system. It's a cryptography system for Windows that is tightly integrated with the file system. Okay, and encryption and decryption are transparent to the user, so they don't see what's going on. Okay, and that's an important point. That's run literally like behind the scenes. So if you encrypt the whole disk, the whole hard drive, wow, that's called full disk encryption. It protects all the data on a hard drive. Now, the unfortunate aspect of this, I'm going to take a deviate here. Later on, we're going to talk about ransomware. And one of the things that some ransomware does, it'll encrypt your hard disk with full disk encryption and then say, okay, I'll give you the key only if you pay me money. And that's where that ransom comes in. We'll talk more about that down the road. Full disk encryption, it protects all the data on a hard drive. An example, BitLocker drive encryption software. It's included with Microsoft Windows. BitLocker encrypts the entire disk, including the Windows registry. So if somebody were to break into the computer, they wouldn't be able to make any sense out of it. It'd be all gibberish. You have volume-leveled encryption, protecting a volume, which is technically a section of a drive that's accessed by a user and has a file system associated with it. You have your database level encryption. It occurs with one of two ways. The plug-in method requires attaching an encryption module into the DBMS. Transparent data encryption executes encryption and decryption within the database engine itself. And transparent data encryption does not require any additional packages or code modification of the database engine or DBMS, and it's easier to manage. Then you also have hardware encryption. Those use things that are dongles that basically plug in like a USB drive, or in the old days they had one that plugged into the printer port, and so on and so forth. Most of the days now they're USB drives or USB devices or standard hard drives. So this is cryptography that can be embedded into hardware. It's almost like firmware, but it's a special type of cryptography software. Cryptographic features can be built into the hardware of a USB drive, which then allows for all the data written to that be automatically encrypted. Some hardware-based USBs allow administrators to remotely prohibit accessing the data, or lock out the user, or even instruct the drive to initiate a self-destruct. Almost sounds like that movie, what was it, Mission Impossible? So if someone unauthorized that, they can basically self-destruct the drive, causing a sequence to then destroy all the data on that drive or on that USB device. You have self-encrypting drives. They're drives that can protect all the data written to them. The drive and host device perform authentication processes during the initial power-up. If authentication fails, a drive can then be configured to deny access or even delete the encryption key so all data is permanently unreadable. I hope that's not the case, because then that data is lost. You can't get it. You have a hardware security model. It's a removable external cryptographic device that includes an onboard key generator and key storage facility. It performs accelerated symmetric and asymmetric encryption. You have your trusted execution environment in a secure crypto processor that's internal to the computer itself. You have the Trusted Platform Module. It's an international standard for crypto processors that provide cryptographic services. Your Trusted Platform Module includes a random number generator and full support for asymmetric encryption, and can also generate public and private keys. On Apple and Android devices, this is called a secure enclave. Okay. Blockchain. This is becoming a popular topic. It's a shared immutable ledger that facilitates the process of recording transactions and tracking assets in a business network. And blockchain technology allows the network of computers to agree at regular intervals on the true state of a distributed ledger. A public blockchain, or open public ledger, is a blockchain network that anyone can join and become part of. A private blockchain operates on a closed network. A federated blockchain, like a consortium blockchain, is typically used when organizations need both a private and public blockchain. So here's what it might look like if you did a diagram. You have multiple organizations with different ledgers. So you can see it's almost like distributed computing, but in this case, this is distributed across multiple plate locations. Here's multiple organizations using a single ledger. So there are limitations of cryptography. It's a necessary feature to add to protect low-power devices and applications with fast response times to make them secure. Adding cryptography to low-power devices or to those that have fast response times can be difficult. So cryptographic algorithms require both time and energy, which results in a resource versus security constraint. So remember I mentioned that's an important aspect. If you're starting to add security versus speed, or in this case security versus something else that you're comparing. There are attacks because everybody wants to know everything about everybody else. So if you got the door locked, that's only going to want to make me try harder to break in. That's what some of these attackers will say. Two of the most common cryptographic attacks use algorithm attacks and collision attacks. Most method attackers can circumvent strong algorithms, include known cipher attack and downgrade attacks. So let's take some of these and look at them. A downgrade attack, say I have my system set for like 2048 or 4096. Let's say 2048 bit in security, or 1024. So you know that's going to have lots and lots and lots of possible keys, and that can be generated and used in that system. What if it's simple as that? The level 1 encryption, maybe just using 40 bits or 80 bits or 128 bits. So if I can get you to lower your encryption from 2048 or 1024 to something less, would you consider doing your presentation or doing your an encryption on that? And that's important because What that does is the attacker is causing you to use a weaker encryption system and one that's easier to break. Just like if you ever played a crossword puzzle, a 3-word word is easier to figure out than a 5-letter word. A 3-letter word is easier to figure out than a 5-letter word. So attackers can use different tools and methods. The first is like statistical tools. So again, just like if you're doing that crossword puzzle, you know that if you got like 4 down and 5 across, if where those letters overlap, that's one letter you don't have to figure out. But if you're in this case trying to figure out the information from the ciphertext, you need to be able to figure that out. Okay, and you can do that sometimes with what are called statistical tools. So I know in the English language, most all the words are going to have a vowel of some kind. There are very few words. There are some that have only consonants in there. So if I guess, that's why I like when you play the game Hangman, you guess the letter A, E, I, O, U. And oftentimes you'll get a letter of that word. In a collision attack, it's the attempt to find 2 input strings and a hash function that produces the same result. So you could have a password like very, very strong password, or one that's like supercalifragilisticexpialidocious or whatever it might be. And when it hashes down, it creates a particular value. Let's call that value X. Now just say I put in unlock the door, or PASSWORD. There is a principle that says 2 or more words or plain text will hash or become ciphertext and generate the same ciphertext. So supercalifragilisticexpialidocious, open the door, a very complicated password. So you can see here a birthday attack is based on a birthday paradox, which says that for there to be 50% chance that someone in a given room shares your birthday, 253 people would need to be in that room. Okay. So when you're using quantum computing, it relies on the quantum physics to use an atomic scale unit, or qubits, Q-U-B-I-T-S, that can be both 0 and 1 at the same time. It's possible for one qubit to carry out 2 separate streams of calculations simultaneously. Quantum computing also has the drawback for cybersecurity. A single quantum computer could perform factoring by using hundreds of atoms in parallel to quickly factor huge numbers, and rendering all current atoms in a parallel asymmetric cryptographic algorithms useless. Post-quantum cryptography algorithms are secure against an attack by a quantum computer. Alright, here's our next knowledge check. Which type of encryption would protect all data on a hard drive? All data on a hard drive. Is it an FDE, SSED, TXPM, or HRHS? So if you remember, they're starting to use initials instead of these long words. But your full disk encryption, your FDE, is going to be the one that you want to look at. To protect the entire hard drive using cryptography, it's known as full disk encryption. And it protects all data on a hard drive, including the installed OS. Okay, so here we reached the end of the chapter. So rate yourself on the competence of the following module objectives. Define cryptography. Define hash, symmetric, asymmetric, cryptographic algorithms. List the various ways in which cryptography is used, and explain the different cryptographic limitations and attacks. Okay, this is our summary, and we have reached the end of this chapter. Okay, have a nice day. I will see you in the next chapter.